This is VLSI data conversion circuits, lecture 59. In the last class we were investigating ways of making the performance of a D2A converter which is embedded inside a delta sigma loop to be free of distortion, and the basic reason for the increase in the noise floor and harmonic components when the elements or the unit elements inside the DAC are not matched properly is that the individual bits that drive the unit elements are nonlinear mappings of the input sequence, right. Conventionally what is done is you take the input sequence, decompose it in a thermometer fashion, and each one of these lines goes and drives a unit element and you add the outputs of the unit elements. Now what happens in practice is that since the unit elements are all not properly matched, the when there are individual when the individual drive waveforms have distortion and noise floor increase, which is bound to happen simply because these individual drive waveforms are derived from the input sequence through some nonlinear transformation, right. So last time we saw that, for instance, the lowest bit of the thermometer code remains on pretty much most of the time, right, whereas the highest bit in the thermometer code only goes high when the input waveform touches the peak, correct. So these are, since these transformations, that is from the input sequence to the individual drive waveforms of the thermometer code, these are fundamentally nonlinear, which means that if you take the input spectrum which is noise shaped, right, that is the input sequence that is being fed to the DAC, right, and that you can assume to be, if you assume to be a nice noise shaped sequence with a very high in-band SNR, the moment you take this sequence and process it nonlinearly to get each one of these thermometer drive bits, the spectrum of this, each one of these drive sequences will have an elevated noise floor and a lot of distortion. There is nothing wrong with this, this is what you should get because these transformations are nonlinear. However, since the input sequence has been decomposed exactly into these thermometer sequences, by construction we know that the sum of these thermometer drive sequences is equal to V, which means however nonlinear these individual thermometer drive sequences are, when you add them together the spectrum must have a very high in-band SNR because that is the way we have constructed it, correct. Now if the weights of the unit elements were all exactly equal to 1, in other words if there was no mismatch, even though you add up all these horrible waveforms with lots of harmonics and noise floor in the signal band, when you add them all up those harmonics all go away because they cancel, and similarly the high noise floor also goes away because of this magic combination of these waveforms, right, which when added together must in principle give you the same spectrum as the noise shaped sequence. Unfortunately, if these unit elements are mismatched, the cancellation is not perfect. So whatever effects you see in the individual waveforms, namely a rise in the distortion as well as a rise in the noise floor, okay, will leak to the output by some factor because the cancellation is not perfect, right. Clearly as the cancellation, as the matching becomes better and better, in other words when the mismatch becomes smaller and smaller, the cancellation becomes more and more perfect, and you will, in the limiting case that mismatch is 0, you will get something which tends to the ideal linear spectrum, the spectrum of the input sequence that you are indeed looking for. Does it make sense? Okay. So the culprit therefore, okay, is the fact that the individual waveforms that drive the unit elements are derived from the input sequence in a nonlinear manner. So, a fix therefore would be to say I am not going to derive these individual drive waveforms non-linearly. If I derive them in a linear way, then by definition if you derive them, if they are linearly related to the input, there will not be any harmonics. Okay. So, when I combine them, I should be able to eliminate distortion and hopefully noise flow. You understand? So, the first attempt in that direction is simply randomization, which is what we discussed in the last class. If this is the conventional thermometer decoded DAC, we said this is a 4 level DAC. So, there are 3 unit elements. If V was equal to 1 conventionally, you would always see that the lowest I mean these elements would always be selected. On the other hand, when you do random element selection, you find that on an average each element is selected at 2 times over 6, or in the more general case the average duty cycle of each element is the same and will be equal to whatever V by number of levels minus 1, correct. So, the mean of each of these elements, alright, will simply be equal to V divided by n level minus 1, okay. And then we saw last time that if you find the autocorrelation sequence, it will give you, I mean the autocorrelation of each of these drive sequences, it will give you something which is the autocorrelation of the input sequence V divided by n, right, plus white noise, okay. So, needless to say, when you find the spectra of the individual drive waveforms, we see that they all consist of the signal in the same amounts, right. This makes sense because on the average every unit element is contributing equally to the output, correct. This is in contrast with a thermometer decoded version where some unit elements are contributing more and others are contributing less, you understand. So, when you add all these up without any mismatch, this is what you should get, and this is the spectrum of the underlying V that you have supplied to the DAC, alright. Unfortunately, if there is mismatch, you will see that the cancellation is only partial, and therefore, the uncancelled part will bear the same spectral shape as this noise. Does that make sense? Okay. So, the total in-band noise is a combination of two things. One is the uncancelled noise due to mismatch plus the quantization noise, and clearly if the quantization noise is way below this mismatch noise, you will be limited by mismatch. And as you can see, the penalty is actually quite a lot. So, if you say that this is the average kind of noise floor in the signal band, you see that with mismatch even after randomization you are about 30 dB worse, that is 5 bits worse, alright. However, what we saw was that when compared to not doing anything at all, you are better off randomizing because the distortion components have gone away, alright. And I mean please note that since this is a log scale, if you find the SNDR in this signal band for instance, you will find that you will be, for the case where you do not do anything at all, you will be limited by distortion because this peak is about whatever on the average some 60 to 80 dB above the quantization noise flow, right. So, pretty much the SNDR will be the ratio of those two, because the rest of it, all this is so small compared to this spike that I mean they do not really effectively add to anything in the noise plus distortion term. Does it make sense? Alright. So, with randomization you have greatly, I mean you have greatly improved the situation with respect to not doing anything at all, right. Now, you start to get greedy and say all I am doing is generating each thermometer drive waveform to be 1 by or V by n level minus 1 plus some other error sequence, correct. You understand? Please note that each thermometer drive waveform now is a 2 level waveform, right. For example, here it is T1 is 1 0 0 0 1 0, alright. It is a 2 level waveform whose average value is the same as V by n level minus 1, right. Apart from this average value, it has got some other waveform, right, and that other waveform happens to have a white spectrum. So, in the presence of mismatch, a part of that white spectrum comes through, okay. So, now this spawns the idea, hey, what if this other sequence, right, we of course for each thermometer drive waveform we want this V by n level minus 1, correct. But and you know, once you understand this, it seems a pretty straightforward thing to say, hey, can I make, I mean the problem with the solution we have as for now is that we are getting rid of the distortion as we want, however the in band noise floor is white and you know is large. So, the question now is, if I make this so called extra stuff, right, have a spectrum which is or which has very little frequency content at low frequencies, then even if there is mismatch, it should not matter too much, or it should matter to a lot less degree than with simply pure randomization. Does this make sense? Okay. All right. So, all right. So, one way of doing this, the aim therefore is to make each thermometer drive waveform a linear function of V, all right. And T I of n minus V of n by n level minus 1 how must this look like? Must have very little power in the signal band. In our case, the signal band happens to be at low frequencies. Okay. All right. So, and please note, I mean this might sound cliched, but T I of n is a what kind of sequence? Is it an any arbitrary sequence, or are there some restrictions on T I of n? It can only take 2 values, okay, is a 2 level sequence. This is a very important, all right. So, Now, in other words, we want a 2 level sequence whose low frequency value is the same as at low frequencies this must resemble pardon. No,
it should resemble V.
V by n level minus 1, correct, all right, and must have and the rest of it. So, in other words, T I minus V by n level minus 1 as we just said, let us say for argument's sake must go as or spectrum must be shaped by say 1 minus Z inverse. This is the simplest thing you can think of where there is no spectrum at, there is no power at DC, and at low frequencies it is small, is not it. So, can you think of what do you think will achieve this? Pardon? A first order? A first order delta sigma converter. So, this is V by n level minus 1, correct, and then if I want 1 minus Z inverse, I mean I need a 2 level sequence, right. So, what do? You take the 2 level sequence, you compare you compare it with V by n level minus 1, you subtract the 2 and you integrate this at low frequencies and use that to drive the quantizer, correct. So, this should give you on the average V by n level minus 1 plus some shaped quantization noise, let me call this some E1 times 1 minus Z inverse. This becomes T1. The Z1 is the so called is nothing but the difference between T1 and the output of the accumulator. Does this make sense? All right. Now, if I what should I do to get T2? Well, okay. So, and T3 and T4 and T5, what should I do? Well, okay. So, the suggestion is that if you have in our example if you have 4 levels, you will have 3 unit elements. So, one thing you can say is okay, I am going to make 3 such loops like this, right, and get T1, T2 and T3 and apply them to the 3 unit elements. Okay. So, is this okay or no, what is the problem?
It will generate the same sequence and all.
Yes, so what?
All of them. So,
okay, then what he is pointing out is that hey, why do you want to have 3 different delta sigma modulators? feed the same thing to all of them. So what happens? What is that becoming? No. What is wrong with what? So far everything seemed logical, right? And all of you are nodding your heads without disagreement. What is wrong with this? Pardon? Yeah. So what? So the average value of T1 is V by n level minus 1, right? If you take 3 of them, the average of the output will be V. First of all, is this insensitive to mismatch or is it sensitive to mismatch? Insensitive to mismatch. Okay. And why do you think it is insensitive to mismatch?
Because T1, T2, T3 they are linear functions of.
Okay. All right. Okay. So if you didn't know all of that, can you look at it straight away and say this got to be insensitive to mismatch? No, if T1, T2 and T3 are all identical, right, then the output waveform of the DAC will be all either 1 or it will either be n or it will be only a 2 level sequence, correct? You understand? And what is that? If you have a 2 level sequence, what is it becoming? What is the equivalent? It is becoming a 2 level DAC, it is becoming a single bit DAC, right, which we know by definition is insensitive to mismatch. Okay, but what is the problem?
No, you have to satisfy to.
No, don't jump ahead. What I am asking is, what is the problem with making it a single bit DAC?
ADC is a multi-level this thing and feedback is just one. Yeah.
That is perfectly fine, right? You just throw away many levels of the ADC and then you have only.
Are we going to run the DAC also at the same clocking at the same frequency? Or?
Apparently, right? No, if you take a multi-bit modulator, remove the multi-bit quantizer and put a single bit quantizer, what effect will it have on the output SNR? The quantization noise will increase, right? You understand? So it is true that if you do this, the output of the modulator will be devoid of harmonics, at least in principle, okay, because each one of these waveforms is a linear representation of the input. Unfortunately, the in-band quantization noise will rise significantly because it is now as if you are operating the whole multi-bit, I mean you have converted a multi-bit delta sigma modulator into a single bit one. So, it is not just enough to have an array of what do you call delta sigma loops like this, right, even though each one of these thermometer drive waveforms has is a linear function of the input and the rest of it is shaped and so on. Does it make sense? Okay. So, I mean one more observation to make, as he pointed out, is that the if you look at in this particular case T1 plus T2 plus T3, all right, this will not at all times be equal to V of n. You understand? It will only be equal to V of n on the average. Okay. So, in other words, what you are doing is that if you put this whole thing inside a box, you are sending in V and you are getting out T1, T2 through T n level minus 1. Okay. One important thing to make sure is that just like in the randomized case, what was the sum of these T's at any time, right, like we saw in the randomized case. So, this is the mismatch tolerant DAC, right. It is not only important to make sure that these are linear functions of V, it is also important to make sure that at any instant of time T1 plus T2 plus T n level minus 1 must be equal to V, right. So, that in the absence of mismatch, okay, this must simply look like, for example, if there is no mismatch at all, then I mean you must get the what do you call, regardless of what algorithm you use inside, you must get the ideal spectrum that you want. Does this make sense? Okay. Now, so one approach to do this is something that we are aware of from many contexts, right. Is you take a complicated problem and make it into a less complicated problem, and then you apply this recursively, and then you eventually end up with I mean whatever the simplest thing you can solve, and then you are done. You understand? For example, search. If you want to search for something in a big heap, you divide it into 2 heaps, right, and then you search, you divide each of these heaps into 2 smaller heaps, and then even smaller heaps, and so on, until you eventually find what you are looking for, isn't it? So, in the same way, assume you have 2 to the m minus 1 plus 1 levels. Okay, this is a technique which will work, right, only if number of unit elements is a power of 2. Okay. So, if the number of unit elements is a power of 2, the number of levels must be I mean of course it must be an integer, right. If the number of unit elements is a power of 2, how many levels must we have? A power of 2 plus 1. How many bits do you need? What is the smallest number of bits you need to be able to represent so many levels? 2 to the m minus 1, right, plus 1 level. What is the minimum number of bits you have to use to represent? You need m bits, correct. Of course, I mean it is almost a m minus 1 bit number, okay, but since you have 1 extra, you do need 1 extra bit. Does it make sense? So, let us assume that you have 2 to the m minus 1 plus 1 levels, so that, and the motivation for this is that the number of unit elements is a power of 2, okay. And why, I mean what is the motivation to have unit elements being a power of 2? Why do you think? Yeah, so you are taking something, dividing it into two simpler problems, and each of those becomes two simpler problems. So eventually the number of simplest possible DACs will all have to be multiples of, will have to be a power of 2. Okay. So if you want to have an even number of unit elements, it may follows that the main DAC must have a power of 2 plus 1 bits. Okay. So let us do one thing. We need to split this. Let us say we want to split this into two sequences which are 1 bit smaller, correct. So in other words, V1 and V2 are two sequences which are m minus 1 bits long and the sum of V1 and V2 is exactly equal to V. Alright. Now why does this make sense? Why do you think this constraint makes sense? Why do you think this constraint makes sense? Pardon? No. Okay, forget about what is there inside this box right now. Okay, what I am trying to do is to split this sequence V of n into two sequences V1 and V2. Okay, each of these sequences V1 and V2 occupies m minus 1 bits. All right, you understand? And the reason for doing this, attempting to do this, is that in the next step I will take V1 which has got m minus 1 bits and split it into two DACs, sequences which are m minus 2 bits and so on, eventually until I get 1 bit, right. So this 1 bit sequence can be used to drive a unit element, you understand. Okay. So at every stage, if I allow for not only that these two sequences must be m minus 1 bits, but if I make sure that the sum of V1 and V2 is the same as V, then what will happen eventually? Finally, when you add all the thermometer T1 through Tn level minus 1, that by construction will be the same as V. You understand? Does this make sense? Alright. So if I say that I am going to split V of n into two sequences V1 and V2, where V1 and V2 have one less bit than V, and the sum of them is exactly equal to V. Alright. So that is equivalent to saying that finally if V1 and V2 add up to give V of n, then you can represent, you can represent V1 as V by 2 plus something and V by 2 minus something, correct. So which is also equivalent to saying V plus something by 2 and V minus something by 2. I call that something S. Does it make sense? So, now by construction V1 plus V2 is equal to V, and I need to find some sequence S such that what all are satisfied. So, the basic idea is to split V into two sequences V1 and V2, where V1 and V2 have one less bit, alright, which means that V1, and with the additional constraint that V1 plus V2 is exactly equal to V of n, which means that V1 can be written as V plus some S by 2, and V2 can also be written as V minus S by 2. This way, by construction, the sum of these two is equal to V. We need to find therefore some sequence S such that these resulting sequences are one bit smaller. I mean, if you add any arbitrary sequence S, the sum will be V, but we need to find a special sequence S, right, such that these V1 and V2 are m minus 1 bits long. Okay. Yeah, I will come to that, right. So, we need so clearly V1, V2 and V are all integers, correct. So, if this has to be an integer, it must follow that this must be, if you take something and you divide by 2 and you get an integer, what must be the input? It must be even, right. So, okay, regardless of what V is, after you add and subtract S, the result must be even. Okay, so that when you divide by 2, you will get a sequence which is one bit smaller and is an integer. Now, since V1 and V2 are of this form half V plus minus S of n, one thing you must observe is that these are linear functions of V plus some sequence. Okay. So, if I gave this to an ideal m minus 1 bit DAC and this to another m minus 1 bit DAC, and if I added these two together, okay, will this be insensitive to mismatch between gains of this DAC and this DAC? Pardon?
Sensitive to mismatch between gains.
Think carefully. All I am saying is, let us say I had two ideal DACs being driven by V1 and V2. Let us say these two DACs are exactly identical, the only difference is that this is 1 plus delta 1, this is 1 plus delta 2, and I add the 2. Can you comment on the sensitivity to delta 1 and delta 2 of the combined output? It is a, I am sorry, it is a multiplier. Okay.
Depending on the gain mismatch.
Okay.
Depending on delta 1 minus delta 2.
Okay. So, if, I mean, do you all follow that if there is gain mismatch between these two DACs, right, the output spectrum will be the spectrum of V plus a small residue of whose shape is the same as that of S of n. Is that clear? Okay. So, if you want that shape to have very low content in the signal band, which is at low frequencies, what must you say about what can you say about S of n? What must you say about the spectral shape of S of n? It must have very low frequency, I mean very low power at low frequencies, correct. So, in other words, if you want the noise or the mismatch between the gains of these two DACs, right, to be shaped out of the signal band, right, you must have S of n whose spectrum also has the same kind of noise shaping in the signal band. Does it make sense? So, what exactly are we looking for as far as S of n is concerned? Right, S of n should be, we concluded that these two must always be even regardless of what V of n is, which means that S of n should be even if V of n is even and odd if V of n is odd. This way, when you divide by 2, you will have, I mean, no remainder. Is that clear? Okay. And if you want to make sure that these are exactly m minus 1 bits, you must make sure that V plus S must be less than 2 raised to m, and similarly V minus S must be greater than or equal to 0. So, these two must lie between 0 and 2 to the m minus 1, I am sorry, this must lie 2 to the power m minus 1. That is, these numbers must lie between 0 and 2 to the m minus 1. So, when you divide down by 2, you will get something which lies between 0 and 2 to the m minus 1 minus 1. Does it make sense? And on top of this, S of n must be 0 mean and must have a noise shaped spectrum. Is this clear? So, before we understand how to generate this special of S of n, which seems to have an awful lot of constraints, correct. So, the first thing as a prelude to this, how do you generate a 2 level sequence with 0 mean and whose spectrum goes as 1 minus Z inverse?
I mean, take this first order signal from generator, feed the 0 input.
Yes.
So that means the output, DC output also will be 0.
Okay. So, you have a 2 level sequence. If I have h of z in general and do this, this will give you a sequence with 0 mean, correct, and noise shaped, it will have only 2 levels because the quantizer is enforcing the 2 levels, and it will have a spectrum which goes as 1 by 1 plus h of z. Is that clear? So, if h of z is Z inverse by 1 minus Z inverse, then the spectrum at the output will be 1 minus Z inverse times some quantization error. Is this clear? So, before we get into more details, I just want you to take a step back and see what we have done here, right. All I said was we need a 2 level sequence which has some specified behavior at low frequencies, okay. So, the first thing is to say I am going to have a generator which generates 2 levels, right. Then I compare that 2 level sequence at low frequencies with what I want, which happens to be 0 in this case, right. And because I am only interested in low frequencies, I multiply it up by some h of z which has got a high gain at low frequencies, and if this loop is stable, that is a very important if, okay, all right. If this loop is stable, the output sequence will have a spectral shape which is of the form 1 minus Z inverse. Does it make sense? Okay. Now, the next thing is to say, all right, now how will you generate? So, let us assume that I am trying to generate S, and for argument's sake I am just going to say S is a 3 level sequence which either takes values 1, -1 or 0. I mean, it could in general be more than 3 level sequence, because all that you need to do make sure is that you do not overflow the, V plus S and V minus S should not become, should not go beyond the range 0 to 2 to the m minus 1, correct. But the simplest case perhaps is to say I am going to assume an S of n which is 3 level, -1, 1 and 0. So, I need to generate a 3 level sequence with 0 mean and whose spectrum goes as, for instance, 1 minus Z inverse, and it must also be what are the properties of S? When V is even, S should be even, okay. When V is odd, S should be odd, correct. Here thankfully if we assume that this only takes on levels of -1, 0 and 1, when V is even the output must be even, and the only even integer here is 0, correct. When V is odd, it should be, it can be either 1 or -1, and you want its spectrum to be 1 minus Z inverse at low frequencies. So, so this is some special kind of quantizer, right. You impose more conditions on the quantization, that is all. So, you first have a block which satisfies all your conditions, right. This is exactly analogous to what we did earlier. We have a block which satisfies our conditions were only one, that is you want this sequence to be a 2 level sequence, right. The only departure from that is now that I have a lot more conditions on my sequence, right. It should be 3 level, it should be odd when something is happening, right, okay. Alright, you could also impose a condition that this sequence should be exactly 1 during Rahu Kalam, right, and and that is still okay, you understand, alright, as long as this loop is stable, okay, and you do this, this sequence will have 0 mean and a low frequency behavior which goes as 1 by 1 plus h of z. Is this clear? alright. So, now you will put this all together, this is the sequence generator which generates S of n. By definition therefore, or by construction, this will be 0 mean and will have a shape which goes as 1 minus Z inverse. You add and subtract to V, divide by 2. So, you will get V1 and V2 which are m minus 1 bits long. Okay. So, now we have done this. So, what do you think we should go and do going forward? Copy and paste, except that m now becomes m minus 1, and when you do that you get this. So, let us take an example where there are 5 levels, which is 2 to the 2 plus 1. So, how many unit elements must be there finally? If you have 5 levels, how many unit elements must be there? 4, correct. So, but the 5 levels have to be represented by 3 bits, correct, and therefore, this is after the first time you generate S, alright. This S generator must look at V because it is doing this even odd business, alright, and it generates V21 and V22 which are 2 bits long. The sum of these two must exactly be equal to V by construction. Now, I take V21 and V22 and again have a sequence generator which generates another S, let me call this S1 A and S1 B, alright, and what if there are 2 bits here, this must be 1 bit. So, these are T1, T2, T3 and T4. Okay. So, in the next class we will take a look at the spectra of each one of these thermometer drive signals and see what happens to the overall spectrum. Okay.